Hello everyone. I am Himanshu Mishra and I am PhD research scholar in the Department of Applied Mechanics, IIT Madras. And this week I am going to discuss about some problem related to the heat exchangers by NTU method. So last week I started with heat exchanger problems and solved some problems related to the log mean temperature differences, as well as revised few problems related to the internal heat transfer as well as free heat convection. And so this week we will be usually solving problems related to heat exchanger by NTU method. We will also touch one or one or two problems related to log mean temperature difference. So let's start with the first question here. So first question says that a cross flow air to water heat exchanger with an effectiveness of 0.65 is used to heat water with hot air, and water enters the heat exchanger at 20 degrees Celsius at a rate of 4 kg per second, while air enters at 100 degrees Celsius at a rate of 9 kg per second. So we have given the overall heat transfer coefficient, which is 260 watt per meter square degree Celsius, and we need to determine the heat surface area of the heat exchanger on the water side. And we have given the assumption that both fluids are unmixed. So here we will be using the NTU method to solve this problem. Before solving this problem, we know that if we have not given the temperature, all four temperatures, and so we cannot use the log mean temperature difference, and therefore we need to use one different method, which is NTU method. So there are various correlations of NTU based on whether the heat exchanger is parallel or cross flow or counter flow, and we will be using some of this correlation. So here we have given two details of the heat exchanger. So the first detail is the heat exchanger is cross flow. The second detail is both fluid are unmixed. So that means we need to use the NTU correlation, which is correspond to the cross flow, and we need to take the consideration that both fluids are unmixed. So there are typically three NTU or effectiveness correlation for the cross flow heat exchangers, and it depends whether the fluid is unmixed or not. So suppose we have a cold fluid and hot fluid, which have the heat capacity Cc for the cold fluid and Ch for the hot fluid. And now based on whether they are mixed or not, or both fluid mix or not, or if even one fluid mix or not, there are multiple correlations for the effectiveness. We have given in the question that both fluids are unmixed. So let me share one. So as you can see that we have three correlation for the effectiveness for the cross flow single pass. So in equation 11.32, the effectiveness is shown for when both fluids are unmixed. And similarly, there are equation 11.33a and 0.334a, which are when any one of the fluid are mixed and other fluid are unmixed. So we can get for the mixed flow, if let's say one of the fluids is mixed and other is unmixed, in that case we can get NTU value of NTU for this effectiveness relation. So we have given in effectiveness relation in 11.33 and 0.34a, and we can solve for NTU. But when both fluids are unmixed, So we cannot find NTU from this correlation because of this complicated relation. We have NTU to the power 0.22 and NTU to the power 0.78, and therefore we cannot separate NTU. We cannot find out NTU given that we have provided this effectiveness. So either we need to use some guess to find the NTU value from this expression, or we can use a chart, effectiveness versus NTU chart. Uh, so these are the charts, effectiveness and NTU charts for parallel counterflow as well as for the cross flow heat exchangers. So when the both fluids are unmixed, it is better to look at this chart. And similarly, if one of the fluid is mixed and other is unmixed, then we can use the correlation for the cross flow if we want to find the NTU from the correlation. Otherwise, finding the NTU from the effectiveness correlation, as we have discussed, is not possible from this given expression where the both fluids are unmixed. So there are expressions where effectiveness is a function of heat capacity ratio and NTU, just to be devised. And these relations are given when either one fluid is mixed or both fluids are unmixed. So for the first case, since this effectiveness relation is actually depends only on this ratio of this heat capacity of the NTU, you can find this relation in any of the heat exchanger, heat transfer book. So we can find out the NTU from this relation itself for the first case. But for the second case, the explanation is very complicated, as I was showing in the book. So it is not possible in the second case to find the NTU from this effectiveness correlation, because the NTU is given in terms of some complicated function, and therefore mathematically we cannot get NTU from this relation. So when both fluids are unmixed, we can use charts, effectiveness versus NTU charts, to find the NTU, since we already have given effectiveness in the question. So let's begin. So we first need to find the ratio of the heat, specific heat, ratio of the heat capacity rates, and so we need to find the area. So we will be using the NTU method. So we need NTU to find the area, and for NTU we need effectiveness, which is already given in the question. And in the effectiveness, we are using the graph to find the NTU, and for that we need the heat capacity ratio. So for different value of heat capacity ratio, so let's say my effectiveness versus NTU graphs probably look like this. And each line is correspond to the different heat capacity ratio. And since we already have given this effectiveness, which is 0.65, For specific value of heat capacity ratio, we can find NTU. So if we found the heat capacity ratio is CR, this CR1, then my NTU would be this value. And similarly, if my heat capacity rate is CR3, my NTU would be this value. So for the when both fluids are unmixed, in that case, it is better to use this plot for finding the NTU rather going to solve the correlation given for the effectiveness. So we can find the heat capacity rate for the hot fluid. So the mass flow rate is given as 4 kg per second, and the specific heat is given as 4.18 kilojoule per kg degree Celsius. So I can write my heat capacity for the hot fluid is 16.72 kilowatt degree Celsius. Similarly, I can write for my cold fluid. So the mass flow rate is 9 kg per second, and the specific heat is 1.01 kilojoule per kg degree Celsius. So on solving this, I can get heat capacity rate for cold fluid is 9.09 kilowatt degree per Celsius. So as you can see that the cold fluid has the minimum heat capacity compared to the hot fluid. So my minimum heat capacity is actually the heat capacity of the cold fluid. So heat capacity ratio would be which is 0.544, and the effectiveness is given as 0.65. So we have given effectiveness 0.65, and we have given the value of heat capacity ratio at 0.544, and by using this graph we can find the NTU. So I will write directly the NTU value. You can check later by using the graph. So let me check with the graph myself. So figure 11.12 is my effectiveness and NTU plot for the required problem. Sorry, so figure 11.14 has the plot of effectiveness and NTU for the cross flow heat exchanger. So we have given the value of effectiveness as 0.65, and we found the ratio of the heat capacity rate to be 0.544. That means we have to follow this line here, which correspond to the zero point 0.5. So basically we are just above of this line since we have 0.544. So from this plot we have 0.65 effectiveness, which lies somewhere here, and therefore we can get the NTU somewhere here, which is approximately 1.5. So from the plot we get NTU approximately 1.5. So now we can use the NTU relation, which is quite simple. Which is given as, so here U is my 260 watt per meter square degree Celsius, which is my heat transfer coefficient, and C minimum is my heat capacity of the cold fluid. So we just need to put the value to find this A. So my heat capacity for the cold fluid is 9.09, and overall heat transfer coefficient is 260 watt. So I'm writing in kilo watt or kilo 2.6. So my area would be, on calculating this, my area become 52.4 meters square. So in this problem, we have given the cross flow heat exchanger, and the second condition was given that both fluids are unmixed. We have given the inlet temperature for the both fluid and the overall heat transfer coefficient, and we need to find the area. So we used NTU method here in this problem. So first we identify the correlation, effectiveness correlation given in terms of NTU. And since there are multiple correlation based on whether the fluid are mixed or not, we found that for the unmixed case, it is not possible to find the NTU from the effectiveness correlation, since the expression is very, very complicated. So instead, using that complicated expression for the, and here I'm talking about only unmixed case. For when the fluid is mixed, we can use the correlation to find the NTU. But for the unmixed case, since the correlation is very complicated, we use the plot, effectiveness versus NTU plot. I have shown the plot in the book, and from the plot, we found that NTU is around 1.5. So the basic thing we require to find the NTU is the ratio of heat capacity rate, which we can find very easily. Since the specific heat and mass flow rate is given in the question, we can find the specific heat for heat capacity for the both fluid, and we can then find the ratio of it. Once we get the heat capacity ratio and we already have effectiveness, we can just find the NTU, which is 1.5 for this case, and we can use this simple formula then for the NTU to find the area of the heat exchanger. So let's move to the next question. So in the next question, a thin wall double pipe parallel flow heat exchanger is used to heat a chemical whose specific heat is 1800 joule per kg degree Celsius with hot water 4 joule per kg degree Celsius. So the chemical enters at 20 degrees Celsius and water enters at 110 degrees Celsius. We have given the area, which is 7 meter square, and we have given the overall heat transfer coefficient, which is 1200 watt per meter square degree Celsius. And we need to define the temperature, outlet temperature of the chemical and water. So in this problem, we will be using again the NTU method, since the outlet temperature of both chemical and water is unknown. So basically we cannot find this outlet temperature by using the conventional logarithmic temperature difference that we have used in the last week. So by using the NTU method, first it is given that the heat exchanger is parallel type. So to find the temperature of the outlet, we will be using the heat transfer relation for both cold and hot fluid. And to do this, we need to find heat transfer itself. Yeah, so we need to find the heat transfer itself, and the heat transfer, for finding this heat transfer, we will be using the effectiveness, which can be given as ratio of heat transfer with the maximum heat transfer. So for the maximum heat transfer, we don't need to use the outlet temperature of both the fluid. So we can find this maximum heat transfer just by the information given in the question. So we have already given the inlet temperature of both the fluids. So from them we can get the maximum heat transfer. And we need to find the effectiveness also, because using this relation we will be finding Q, and from Q relation, which is typically a heat transfer relation, we will be finding the temperatures. To find the effectiveness, we will be using the correlation based on the parallel heat exchangers, which is suitable for the parallel heat exchangers. So let's find the heat capacity rate first. So for the hot water, mass flow rate for the hot fluid is 2 kg per second, and specific heat is 4.18 kilojoule per kg degree Celsius. So on solving, the heat capacity for the hot fluid will be 8.36. Similarly, the heat capacity for the cold fluid and the mass flow rate for the cold fluid is, and the specific heat is 1.8. So on solving this, I will get the heat capacity for the cold fluid will be 5.4. So now we can see that my minimum heat capacity value is of the heat capacity of cold fluid. So my heat capacity ratio will be just on solving this we get 0.646. So my maximum heat transfer will be temperature difference of both inlet temperature. So here I am using the inlet temperature of both hot and cold fluid. So the temperature of hot fluid is given as 110 degrees Celsius. This is my inlet temperature. And my inlet temperature of the chemical, which is a cold fluid, is 20 degrees Celsius. And we already found the minimum heat capacity, which is heat capacity of the cold fluid, which is 5.4 kilowatt per degree Celsius. So on solving, I will get maximum heat transfer. This is my maximum heat transfer, 486 kilowatt. So now we got this maximum heat transfer, and to find the heat transfer we need this effectiveness as well. So we will be finding this effectiveness. We will be using the NTU correlation, effectiveness NTU correlation correspond to the parallel heat exchanger. So NTU can be, so we know this formula for NTU. So we have given overall heat transfer coefficient, we have given the area, and we already found out the heat capacity of the cold fluid, which is minimum heat capacity. My area is 7 meter square, and this is my heat capacity of the cold fluid. So on solving this, my NTU will be 1.556. Now I will be using the effectiveness correlation for the parallel heat exchanger. So my effectiveness relation will be this is my effectiveness correlation. We already found out NTU. We actually found out the ratio of heat capacity as well. So my ratio is 0.646. So on calculating this expression, we will get the effectiveness of 0.56. So we now found the effectiveness. We already found the maximum heat transfer, and then now we can find the heat transfer, the actual heat transfer that is take place in the heat exchanger. This will be my effectiveness. So my actual heat transfer will be the maximum heat transfer that we found is 486 kilowatt. So 272.2 will be my actual heat transfer. So now we can find the temperature using simple Newton's law of cooling. Just a standard heat transfer relation. So if we want to find the temperature of outlet of the cold fluid, I will be using the heat transfer relation for the cold fluid. So it is basically a difference of temperature of outlet of cold fluid and inlet of cold fluid and my heat capacity of the cold fluid. So we need to find the outlet we need to find the outlet temperature of the cold fluid. So this can be given as Q is my 272.2 and my heat capacity for the cold fluid, which is my minimum heat capacity also, is given by 5.4. Both are in kilojoule quantity and my temperature of inlet is 20 degrees Celsius. So on calculating this, I will get temperature outlet of cold fluid is 70.4 degrees Celsius. Now we can use a similar exercise to find the temperature of hot fluid at the outlet. So this is my temperature of hot fluid at the inlet and this is my temperature of hot fluid at the outlet and this is my heat capacity for the hot fluid. So my heat transfer will be the same. So specific heat for the hot fluid we found is 8.36 and the inlet temperature for the hot fluid is 110. So my outlet temperature of the hot fluid becomes 77.4 degrees Celsius. So in this question we have given the parallel flow heat exchanger. We have given the two inlet temperature of the fluid, one for the inlet temperature of the hot fluid and inlet temperature of the cold fluid. We have given the heat capacity, specific heat rate and the overall heat transfer coefficient rate as well. So, and we need to find the outlet temperature. So for the outlet temperature, we can use the standard heat transfer relation, which is the difference of the temperature of the fluid at the inlet and outlet. So for that, we need to find the heat transfer itself. And to find the heat transfer, we use the effectiveness relation, that is, which is given by ratio of actual heat transfer and the maximum heat transfer. Now we can find the maximum heat transfer because it requires only the inlet temperature of hot and cold fluid. So we found first maximum heat transfer, and then we using the parallel correlation for the parallel heat exchanger, we found the effectiveness as well. Now make sure that to find the effectiveness you need NTU, value of NTU as well, which is can be found out using this relation. It's a simple relation, and once you get effectiveness and the maximum heat transfer, you will get the actual heat transfer also, and from the actual heat transfer relation, it is easy to find the temperature. So let's move to the third question. So in the third question, the water enters the internal diameter tube of double pipe counter flow heat exchanger. It is entering at 17 degrees Celsius. Water is heated by steam condensing at 120 degrees Celsius in the shell. Overall heat transfer is given as 900 watt per meter square degrees Celsius. And we need to determine the length in order to heat the water to 80 degrees Celsius. So 80 degrees Celsius is the outlet temperature of the water, and we need to find the length of the tube using both log mean temperature difference and by using NTU method. So first we will be solving this problem by log mean temperature difference. So such problems we already solved in the last week. So this will be quite recap problem. So we are given the counter flow heat exchanger. So for using the log mean temperature difference, we know that we need to determine the delta T1 and delta T2. So for the counter type heat exchanger, delta T1 is the difference between the inlet temperature of the hot fluid and the outlet temperature of the cold fluid. Similarly, the delta T2 is the difference of outlet temperature of the hot fluid and inlet temperature of the cold fluid. So my delta T1 is 40 degrees Celsius and delta T2 is 103 degrees Celsius. Now we can find the log mean temperature. So my log mean temperature is 66.6 degrees Celsius. So earlier we find the log mean temperature difference and then we begin to find the dimensions of the heat exchanger. So to find the dimension, we will use this expression. So last week we have used this expression to find the area or the length. So we have already given the overall heat transfer coefficient. We already found the log mean temperature difference, which is 66.6, but we don't know the heat transfer rate. So since we have given the outlet temperature of inlet and outlet temperature of the cold fluid, we can use the standard relation. So this relation we actually used in our previous problem also. So heat capacity for the cold fluid will be mass flow rate of cold fluid multiplied by specific heat of the cold fluid. So I am writing in kilojoule quantity. So my heat transfer will be 790.02 kilowatt. So we found the heat transfer also. We have given this and we found this. So my area would be pi dl and we need to find the length. We already given diameter. So my length will be my overall heat transfer is given as 900 watt per meter square degree Celsius. Which is 0.9 in kilowatt, and the diameter is given as we found the log mean temperature difference is 66.6. So now on solving this, my length would come out as 167.8 meter. So we found the length using log mean temperature difference. So this is quite similar calculation we have performed last week also. Now we will be finding the length using the NTU method. So just to recap, we actually use the heat transfer relation to find the length or the dimension of the system. So we need first log mean temperature difference, and we need the overall heat transfer coefficient, and we need this heat transfer rate. So we have already given this, and to find the log mean temperature difference, we need to use the delta T1 and delta T2, which is for the counter type heat exchanger. It is just a difference between the hot inlet temperature and the cold outlet temperature, or the hot outlet temperature and inlet cold temperature. Once we found this difference in the temperature, it is easy to find the log mean temperature by using this relation. Once we get the log mean temperature, our next step to find the heat transfer rate, because otherwise we cannot use this relation because there will be two unknown, AS and Q. So for finding the heat transfer relation rate, you need to see the temperature data which is given in the question. So we have given the outlet and inlet temperature of the cold fluid. So we use this relation, standard relation for the heat transfer. Let's say we have given the temperature data for the hot fluid, let's say outlet temperature of the hot fluid and inlet temperature of the hot fluid. Then you may have used that relation for the hot fluid, in minus pH out, like that. So from this relation you find out Q, and once we get Q, it is we use the log mean temperature heat relation to find the heat this dimension of the heat exchanger. Now we will be using the NTU method for solving the length. So again we need actual heat transfer rate to use the NTU method, and we already found that because we given the temperature of inlet, cold fluid at both inlet and outlet. So we already found in our previous part, which was 790.02 kilowatt. And we can find the maximum heat transfer as C minimum So for the maximum heat transfer, as we discussed in previous question, that we record an inlet temperature of both hot fluid and cold fluid, and we have given the C minimum as 3 mass flow rate multiplied by specific heat capacity. So we know that the effectiveness will be given as ratio of actual heat transfer to the maximum heat transfer, which is so I will get effectiveness of heat exchanger as 0.61. So you can recall from the previous question that we first found the effectiveness and then we found the actual heat transfer. But here we first found actual heat transfer, and then we found the effectiveness. Now, from the NTU relation, since we have given that the water is heated by steam condensing, so for the condensation and evaporation problem, the NTU correlation will be quite different. So you can check both. There will be a list of correlation which is given for the condensation, evaporation, as well as parallel, counter, cross flow, various kind of situation. So for in our case, I will be using this relation. So we already have effectiveness, which is 0.61. So my NTU will be 0.942. Now, once we got the NTU, we just need to find the area. We have already given overall heat transfer coefficient. We already found out the heat capacity of whole fluid. So this is my area. So I just need to put the values, and I will get my length is 167 meter. So for the first part, we use log mean temperature difference. So I got my length as 167.8 meter. Now by using the NTU method, we got length as 167 meters. So which is correct. So let's move to the next question. So the next question is true and false question. So the first question says that the value of effectiveness ranges from 0 to 1. It increases rapidly with NTU for small value but rather slowly for large values. Therefore, the use of heat exchanger with large NTU and with a large NTU and thus large size cannot be justified economically, since large increase in NTU in this case correspond to the small increase in effectiveness. So in first question, it says that for the lower value of effectiveness, the NTU will be increases much more rapidly, and when the NTU is very large, then effectiveness won't increase much, and we should not use heat exchanger with large number of NTU. So this is actually a correct statement, because we know that so for different cases the effectiveness, so for different types of heat exchangers like parallel, counter, cross flow, and different situation like double shell, single shell, like that, my graphs usually look like this. This is my typical graph effectiveness versus NTU plot for different kinds of heat exchangers. And we can see that for the lower value of effectiveness, that means here, my NTU will be increasing rapidly, but for the higher value of NTU, so as we go right in the NTU axis here, we see that there is very marginal increment in the effectiveness. So even at larger value of NTU, it almost looks like a constant. It actually increases very, very slowly. So for the smaller value of NTU here, there is a rapid increment in the effectiveness value. You can see that here. But here there is very slow marginal increment of the effectiveness value. And since you are using the heat exchanger for the heat transfer purpose, the first objective when you design the heat exchanger is that it should have high effectiveness. That means it should actually transfer maximum heat out of the system. So that means your effectiveness will be higher if there will be maximum heat transfer. So you always wish to have a maximum heat transfer rate, but here we can see that at larger NTU there will be no rapid variation of rapid increment of effectiveness. That means there will be no maximum heat transfer that usually occur. So we will be using heat transfer which have the NTU in this range, which is pretty with pretty less NTU value. Because in that case range, the effectiveness will be much uh, varying or much it will be quickly increased. So the first statement is correct. So in the second statement, it is said that for the given NTU and the capacity ratio, the counter heat exchanger has highest effectiveness, following the closely by cross flow and with both fluid unmixed. The lowest effectiveness value are encountered in parallel heat exchanger. So which is actually quite correct statement. So you can check this effectiveness and NTU plots for different types of heat exchangers, and you can find that the effectiveness of heat exchangers is usually greater than effectiveness of cross type heat exchanger, and for the parallel type the effectiveness is usually very lower comparatively. So my both statement is actually correct. So the correct option is A here. So let's move to the different question. So in this question we have given double pipe heat exchanger constructed from steel having the thermal conductivity of 15.1. Inner tube have inner diameter and outer diameter is given, and for the outer shell inner diameter is given, and my inlet heat transfer coefficient is given as HI 800 on the inner surface, and at the outer surface it is 1200 as H0. The fouling factor is given as 4 10 to the power minus 4 meters per Kelvin per watt, and the outlet fouling factor is also given. So we need to determine the thermal resistance. So usually we use the fouling factor when there is a deposition of some impurity inside the heat exchanger. In that case, we need to consider the resistance of the fouling factor. So we need to find the thermal resistance. So we have given the inlet and outlet heat transfer coefficient. So that means there will be a resistance due to inlet and outlet heat transfer coefficient. And there will be resistance from the fouling factors as well. And then we have given the thermal conductivity of the steel. That means there will be some resistance from steel also. So such to find the overall resistance, we actually solves this kind of problem in our previous weeks. But at that time we did not discuss anything about the fouling factor. So I can write down my resistance due to internal heat transfer coefficient as 1 by HA. We know this, and I can write down the resistance due to outer heat transfer coefficient as this is my resistance due to conductivity, thermal conductivity of the steel. Since we have a cylindrical pipe, it will be and my resistance due to fouling factors. We have given outlet and inlet fouling factor, so it will be direct for inlet fouling factor, and this is for my outlet. So this is my overall resistance. And we have given the diameter also. So area at inlet and outlet can be defined by the usual relation. So we just need to put the values here. And after putting the values, we will get total resistance is 0.053 Kelvin per watt. So this is quite straightforward question. So we already have given the heat transfer coefficient at outlet and inlet and thermal conductivity Fouling factors. And we just need to identify the resistance by these inlet and outlet heat transfer coefficient, conductivity, and the Fouling factor. And we just club these together to find the overall heat transfer, overall resistance due to the conductivity and the heat transfer coefficient. So let's move to the next question here. So in the next question, there is a counterflow double heat exchanger having the heat inlet of water temperature and outlet of water is given as 20 and 80 respectively. Mass flow rate is 1.2. The heating is to be accomplished by geothermal water at 160, and we have given the heat diameter as well as the heat transfer coefficient 640, overall heat transfer coefficient, and we need to define the length. So it is quite a similar problem that we have previously solved today in question 2, I think. So again, we will be repeating the same procedure. We have to find the effectiveness. We have to find the maximum heat transfer, and for the maximum heat transfer, we need to find the ratio of specific heat capacity rates. So this is my heat capacity rate for the cold fluid. And this is my heat capacity for the hot fluid. So we already have done this. So we know that the ratio would be C minimum and C max. So my minimum heat capacity is of cold fluid 5.02. So my ratio would be 0.583. Now I can find maximum heat transfer. So as I told, for the maximum heat transfer, we need the inlet temperature of both the fluid and the minimum heat capacity rate. The inlet temperature of both fluid is 20 and 160. So my maximum heat transfer is 702.8 kilowatt. Now, since we have given the inlet and outlet temperature of the cold fluid, we can use the heat transfer rate for the cold fluid. Find the actual heat transfer. So heat capacity for the cold fluid is 5.08. And then solving my actual heat transfer is 301. So now I can find effectiveness. My maximum heat transfer is 702.8. So the effectiveness is 0.428. So once we got effectiveness, we know we will be using the correlation to find the NTU. So we can use either plots or correlation to find the NTU once we got the effectiveness. And depending on the type of heat exchanger given in the question, whether parallel, cross or counter current, we will be using the correlation. So I will be using correlation this. So this will be my correlation. So C is my ratio of heat capacity, which is 0.583. So solving this, my NTU will be 0.651. And once we get the NTU, it is very easy. We will be using the standard relation of NTU to find the area or the length. So just put the values here for NTU and other parameters. The length is 108 meters. So this is quite repetitive question. And just to recall what we have done again, if we have to use the NTU to find the area or the geometry of the heat transfer, you can see this going reverse. If you want to use the standard relation to find the area or the geometry of the heat exchanger, you need first of all NTU and the heat capacity of the fluid. Now to find the NTU, you need the effectiveness. And you can find the NTU by either using some correlation or by using the graphs or charts from the book. And to find the effectiveness, you need the maximum heat transfer and the actual heat transfer. For the maximum heat transfer, you need the inlet temperature of either hot fluid or the cold fluid. And to find the actual heat transfer, you need one inlet temperature of the to find the maximum heat transfer, you need the inlet temperature of hot and cold fluid. And to find the actual heat transfer, you need the temperature of both temperature of either hot fluid or cold fluid. So we have given the both temperature of cold fluid. That means cold fluid out temperature and inlet temperature of the cold fluid, and we can use, therefore we can get the actual heat transfer rate. And to get the maximum heat transfer rate, you need the inlet temperature of both hot and cold fluid. So by taking the ratio, we will get the effectiveness, and then NTU from the correlation or using graph, and then you can use the standard relation to find the geometry. So this is a usual procedure to find the length and area by using the NTU method. We also solved one question where we have used both log mean temperature difference method as well as the NTU method. So the NTU method is pretty standard in every question. We will be finding the effectiveness and the heat capacity ratio by using correlation. We also use graph in one of the question. in the log mean temperature difference, you need to identify first whether the heat transfer is in parallel or counter type, and then you find the temperature difference, and then log mean temperature difference, and then heat transfer if it is not given, and then from the heat transfer relation, you just directly got the area. So we have solved almost every question from the heat exchanger. So last week we have used the log mean temperature difference method, and today we have used the log NTU method to find the area or the dimensions. So next week we will be solving some problems related to the evaporation, boiling, and we will some basics problems related to the radiation heat transfer.